Have you ever stood on the ground and wondered what's beneath you? I mean, really wondered? What if you could just start digging, straight down, and never stop? It's a classic science fiction dream, a grand adventure to the very heart of our planet. But what would that journey actually be like? Forget fantasy for a moment. Let's talk about the real science of digging deep. What happens when humanity points its ambition not towards the stars, but towards the core of our own world? It's a quest filled with incredible challenges and even more incredible discoveries. A story of human ingenuity against the immense power of the planet we call home. The Earth is a layered sphere, like an onion. We live on the very thin, outermost skin of that onion. It's called the crust. It's the solid ground we build our cities on, the rock that forms our mountains, the seabed that hides so much mystery. But this crust is surprisingly fragile when you consider the whole planet. Below it lies the mantle, a vast layer of hot, slowly flowing rock. Deeper still, a liquid outer core of molten iron and nickel sloshing around to create our magnetic field. At the very center is a solid inner core, a metal ball as hot as the surface of the sun. Think about the scale of this. The distance to the center of the Earth is about 6,371 kilometers, or nearly 4,000 miles. That's like driving from New York City to Los Angeles and then some, but straight down. Our entire existence, the history of life, the rise and fall of civilizations, has all played out on this delicate surface. We've sent probes to the edge of the solar system, and telescopes that can see to the dawn of time. Yet, when it comes to exploring our own planet, we have barely scratched the surface. Literally. The journey to the center of the Earth remains one of the greatest challenges we can imagine, a frontier right beneath our feet. This isn't just a thought experiment, it's a real scientific pursuit. Geologists, engineers, physicists, they want to understand what our planet is made of, how it formed, and unlock the secrets of earthquakes and volcanoes, the very forces that shape our world. To do that, they have to go deep, drilling into the Earth's memory, one layer at a time. This quest is not for treasure or a lost world. It's for knowledge. It's for a deeper connection to the cosmic island we inhabit. So, let's begin our descent and see just how far we've managed to go. Before we talk about the deepest hole, let's appreciate some of the other champions of the underworld. Humans have been digging for a long time, for water, for minerals, for shelter. Some of these holes are astonishingly deep. Consider the Bingham Canyon mine in Utah, an open-pit mine over 1.2 kilometers, or 3/4 of a mile deep, so massive you can see it from space. For over a century, miners have carved away a mountain, chasing veins of copper, a human-made canyon that rivals some natural ones. But that's digging wide. What about digging narrow and deep? The Mponeng gold mine in South Africa is the deepest mine in the world. Humans travel down into this mine every day. Its deepest point is about 4 kilometers, nearly 2.5 miles. To get there, miners take a series of elevators in a journey that can last over an hour. Down at the bottom, the rock is hot to the touch, about 66 degrees C or 150 degrees. The mine pumps tons of ice slurry and ventilates constantly just to keep the air survivable. At 4 kilometers, pressure is immense. It's a battle against the Earth trying to crush tunnels shut. And yet, life finds a way. Scientists found a bacterium in deep fractures that lives without sunlight, fueled by radioactive decay of uranium, an independent ecosystem hinting life could exist in extreme places, maybe on other worlds. The undisputed champion of deep drilling is the Kola Superdeep borehole on Russia's remote Kola Peninsula. Starting in 1970, Soviet scientists began a project with a simple, audacious goal: to drill as far as possible into the Earth's crust. Not for oil, not for gold, for discovery. For over 2 decades they drilled, breaking record after record, a geological space race and a source of national pride. The main borehole, SG3, reached 12,262 meters, about 7.6 miles, in 1989. Drop Mount Everest in, and the peak would still be over 3 kilometers below the surface. The hole is shockingly narrow, about 23 centimeters, 9 inches, less a hole and more a needle prick into the planet's skin. But what a prick it was. It penetrated roughly a third of the Baltic Shield continental crust. What did they find down there? Surprises. Lots of them. Geologists expected a transition from granite to basalt at around 7 kilometers, the Conrad discontinuity. It was missing. Instead, the drill kept finding more granite, fractured and saturated with water squeezed from minerals by immense pressure. Fossil water, trapped for billions of years. Most stunning of all, microscopic fossils, 24 species of single-celled marine plankton, remarkably preserved in rocks nearly 2 billion years old. A snapshot of ancient life, miles beneath the surface. Kola didn't just drill rock, it drilled into time, revealing long-locked secrets. The project stopped in the early 1990s, but its legacy still shapes our understanding of the Earth. How do you drill a hole over 12 kilometers deep? You can't just use a giant drill bit. At those depths, the drill string would be impossibly heavy and too hard to turn. Friction and torque would overwhelm any motor. The Soviets invented a new way. Instead of rotating the entire string, only the drill bit rotated, powered by a mud-driven turbine downhole. High-pressure drilling mud flowed through the turbine, spinning the bit, then returned up carrying cuttings. The mud cooled the bit and helped stabilize the hole walls. Drill bits were marvels of material science, complex crowns studded with tungsten carbide and synthetic diamonds, yet a single bit lasted only hours. When a bit wore out, the entire 12-kilometer string had to be pulled and lowered again, a process that could take a full day. Drilling deep is slow, patient, tedious. Another challenge, keeping the hole on course. A tiny deviation at the top means kilometers off at the bottom. Engineers use gyroscopes and magnetometers to navigate, flying blind through solid rock, a delicate dance of power and precision, constantly fighting the immense forces of the planet. Digging deep is a fight against the fundamental physics of our planet. Two colossal forces stand in your way, heat and pressure. As you go deeper, temperature rises, the geothermal gradient, about 25 degrees C per kilometer, or roughly 70 degrees C per mile. Kola's team expected that until the heat increased far faster than predicted. By 12 kilometers, it hit about 180 degrees C, or 356 degrees C, nearly double projections. Extreme heat forced them to stop. Bits, motors, and sensors failed. The rock itself became more plastic, clay-like, flowing and squeezing the hole shut. The Earth tried to heal the wound. Then there's pressure. At the bottom of Kola, it's about 4,000 times atmospheric. Rock compresses, properties change, and high-pressure fluids can blow out into the borehole. Crews countered by managing heavy drilling mud, balancing internal pressure against the Earth's outside pressure. A high-stakes act miles underground. Heat and pressure are the great technological walls that limit exploration. To go deeper, to reach the mantle, we'd need materials surviving hundreds to thousands of degrees and tools that operate where gases become supercritical. We're near the limits of current material science. The Earth guards its secrets well. Why go to all this trouble? Because each core is a page from Earth's autobiography. The rock is a record, chemical and physical, locked away for billions of years. By analyzing cores, scientists see how rocks formed and how heat and pressure transformed them across geologic ages, a time machine through epochs and eons. Kola's cores opened the Precambrian, first 90% of Earth's history. Rocks up to 2.7 billion years old refined models of metamorphism and continent building. A revolution, watered deep in the crust. Not rivers or lakes, but water bound in minerals and microfractures. changing ore formation, earthquake mechanics, and revealing a more dynamic deep Earth. Deep drilling also calibrates seismic images, the planet's ultrasound. Kola showed some seismic boundaries weren't rock types, but changes in physical state from heat and pressure. A vital lesson in how to read the language of the Earth. Once you've drilled the deepest hole in the world, what do you do with it? You listen. The Kola borehole became an underground laboratory. Scientists lowered seismometers, measured gravity and magnetic fields. Listening to the planet's heartbeat from the inside, they detected tiny tremors, micro-earthquakes, activity invisible at the surface, whispers from below that hint at stresses and strains that could lead to major earthquakes. The famous well-to-hell legend, recording tortured souls, is pure fabrication. The real sounds are the groans and creaks of a living planet, moving fluids and rocks shifting under stress. What if we could drill deeper into the upper mantle, the engine of our world? Convection moves plates, continents drift, mountains rise, volcanoes erupt. Sampling the mantle would be geology's holy grail, revolutionizing our models. Projects like 1960's Project Borehole tried through thin oceanic crust, but technical challenges, especially at sea, proved too great. Imagine what we might find: new minerals, clues to the origins of water and atmosphere, even deep chemosynthetic life. So we've drilled 12.2 kilometers. It sounds impressive. It is impressive. It's the deepest we've ever penetrated our own world, but our planet's radius is about 6,271 kilometers. Kola reaches only about 0.2% of the way to the center. If Earth were an apple, our deepest hole wouldn't even break the skin. All our mines, tunnels, and boreholes are faint scratches. We know the mantle and core indirectly, studying earthquake waves, the magnetic field, meteorites, computer models, and high-pressure experiments. Brilliant detective work, but still indirect. To reach the mantle, we'd likely drill through thin oceanic crust, from a ship floating over kilometers of water, then through the moho, where temperatures and pressures spike. The outer core at 2,090 kilometer depth exceeds 4,000 degrees and over 1 million atmospheres. Today, no material could survive that. Subterranean concepts that melt rock demand astronomical power and shielding. We can send a robot 400 million kilometers to roam Mars, but we can't send one 4,000 kilometers straight down. A humbling reality. For the foreseeable future, the deep interior of our own planet may remain more mysterious than distant worlds. We live on a world that is largely unknown to us. We've mapped the Moon and Mars with greater precision than our own ocean floor, and the deep interior remains a realm of inference and imagination. The Kola borehole gave a tiny glimpse, a single sample from an entire world, reminding us our models are incomplete and Earth is more complex than we thought. The quest to dig deep springs from the same impulse that builds bigger telescopes and sends probes to distant planets, the desire to know. These questions aren't just academic. Answers help us predict earthquakes, find resources, and understand climate. Every rock, mountain, and continent is a surface expression of immense slow-motion drama below. Heat from the core and the mantle's churning have driven Earth's entire history, and they're still running. The ground beneath you is a living system, moving, flowing, changing across eons, with secrets still hidden in the depths. So next time you take a walk, think about the 6,000-kilometer journey beneath your shoes, the layers of rock, a sea of molten metal, and the solid iron heart of our world, the immense heat and crushing pressure. What life thrives in the deep, hot biosphere? What new physics and chemistry await when we can build the tools to go deeper?